Today we're going to take a look at the surface area of polyhedra and spheres. So we're going to look at and apply the formulas for the surface area of a sphere. We're going to name regular polyhedra, and then we're going to state and apply the formulas for the surface area of those regular polyhedra. So let's review the definition of sphere. It's a set of all points in space that are equidistant from a given point. So here's an example of a sphere. So all of these points in space are equidistant from this point right here. And we call that point the center. And then we call the segment from the center to any point on the sphere is called the radius. And then a sphere has what we call the great circle. And the great circle is made up of all the radii from the center. So two great circles separate the sphere into four sections, or like four quarters. Kind of think of it like an orange, right? And we call those sections lunas. The surface area of a sphere is 4 pi times the square of a radius. So here is the formula for surface area of a sphere. So S, or surface area of a sphere, is equal to 4 pi r squared, where r stands for the radius. So let's find the surface area of this sphere. So this sphere has a radius of 8. So we'll plug it into our formula. So our formula says S equals 4 pi r squared, where r stands for radius. So we're going to substitute 8 for r. And so now we have 4 pi 8 squared. 8 squared is 64, and then 64 times 4 is 256. So we get the answer 256 pi, which if you multiply 256 times pi, you get approximately 804. However, you can leave your answer as 256 pi. All right, let's talk about regular polyhedra now. So regular polyhedron is a 3D figure, and it has which it means it's a polyhedron, and the faces bounded by congruent regular polygons. So the faces of this 3D figure have to be regular polygons that are all congruent. They have to have the same number of faces intersecting at each vertex. So this is a lot of characteristics, and it's almost a lot of boundaries. So because of that, there's actually only 5 possible regular polyhedra in existence. There's a regular hexagon, so that means that it has 6 sides. And that would be a cube, right? A regular hexagon would be a cube. We have a regular tetrahedron, a regular octagon, and then we have a regular dodecahedron and a regular icosahedron. So a hexagon is made up of squares. A tetrahedron is made up of triangles, but there's 4 of them. An octahedron is going to have 8 sides. A dodecahedron is going to have 12 sides. An icosahedron is going to have 20 sides. So here's an example of these 3D figures. So notice the hexahedron is the only one that's made up of squares. The tetrahedron, which has 4 sides, the octahedron, which has 8 sides, and the icosahedron, which has 20 sides, those are all made up of triangles. The dodecahedron, which has 12 sides, is made up of pentagons. So here's an icosahedron. So an icosahedron, I wanted to show you how we know it's 20 sides. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's just the front. 10 in the front, which means you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the back as well. So that's how it has 20 sides. So the surface area of a regular polyhedron is actually kind of simple to remember. All you have to do is find the area of one of the faces and then multiply it by the number of faces that you have. So our formula is S equals N times A. So S is the surface area of a regular polyhedron equals N, the number of sides, times A, the area of one of the sides. And not really sides, we're actually doing the area of the face, right? Alright, so let's look at an example. Let's say that Blake is selling calendars in the shape of a regular dodecahedron. So remember, that was that 12-sided figure with pentagons on it. To make sure that the calendar for a month would fit on a side, he designed the area of one face to cover 3 square inches. So we know the area of one of the faces. It's 3. We want to find the total surface area. So remember, total surface area is equal to N times A, where N is the number of sides and A is the area of one face. Well, he already told us that the area of one of the faces was 3. And then we know that it's 12 sides because it's a dodecahedron. So we have 12 times 3, which means that our total surface area is 36 square inches. Alright, let's find the total surface area of a regular icosahedron with the edge of 5. So remember, edge does not mean the area of a face. The edge is really just one segment, right? It's just one side. So one of the edges or one of the sides of this triangle is 5. So remember, it's all the faces have to be regular, which means that regular means that all angles and all sides are the same. So if all sides are the same, then that means that this is an equilateral triangle. So if we want to find the area of an equilateral triangle, we can use a formula for that. So remember, the formula for an equilateral triangle is equal to S squared times the square root of 3 over 4, where S stands for the edge or the side. So our side is 5, so we'll substitute 5 for S. So we get 25, because that's 5 squared, square root of 3 over 4. And that's the area of one of the faces. So an icosahedron has 20 faces. We find the surface area, N is 20, and the area is 25 square roots of 3 over 4. So to simplify that, 4 goes into 25 times, and then 5 times 25 is 125. So we have 125 square roots of 3 as our final answer. And then if you were to multiply 125 times the square root of 3, you get approximately 216.5. However, you don't have to multiply. You can just leave your answer as 125 times the square root of 3. Alright, so this is the last lesson in this chapter. So what I would like to do is go ahead and go over all of the formulas for area and surface area that we have learned since the beginning of the chapter. So we started with the area of a square, which was S squared, S standing for one of the lengths of the side, or an edge. Then we learned the area of a rectangle, which was B times H, which B was the base and H was the height. And then we learned the formula for a parallelogram. So the area of a parallelogram was equal to B times H, where B stood for base and H stood for height. So the area for a rectangle and the area for a parallelogram, those were the same. Then we learned the formula for a triangle, which is 1/2 base, or B, times height, or H. Then we learned the formula for a trapezoid, and it was 1/2 H times B1 plus B2, where H stood for height, B1 stood for the first base, and B2 stood for the second base. Then we had a formula for a rhombus, which was 1/2 D1 times D2, where D1 and D2 were the diagonals. And then we had a formula for the equilateral triangle, which we actually used in this lesson, and that was s squared times the square root of 3 over 4, where s is one of the sides or one of the edges. Then we have the formula for a regular polygon, and that was 1/2 a times p, where a was the apothem and p was the perimeter. And then we found the area of a circle, which was pi r squared, where r was the radius. And then we learned surface area. So we said surface area of a prism was equal to L plus 2b, where L was the lateral surface area and b was the area of a base. And then the L we found by doing perimeter times the height. And then we found the surface area of a cylinder, which was S equals L plus 2b, where L was the lateral surface area and b was the area of the base. And we figured out that a cylinder, the bases are circles, so our lateral surface area was found by doing the circumference instead of the perimeter times the height. And then we found the surface area of a pyramid, which was the lateral surface area plus the area of the base. And then the lateral surface area of that pyramid, how we figured that out is we did 1/2 the perimeter times the slant height. Remember? And that was slanted. And then we did the surface area of a cone, which was the lateral surface area plus the area of a base. And that lateral surface area was found by doing 1/2 circumference instead of perimeter times L, which stands for slant height. And again, that was the slanted height. And then in this lesson, we added the surface area of a sphere, which was 4 pi r squared, where r was the radius. And then we had the surface area of the regular polyhedron, which was equal to n times a, where n was the number of faces and a was the area of one of those faces. All right, go ahead and try some problems on your own.